Okay, so this is part two of Get to Know Your Data Booklet. And we stopped yesterday on bond enthalpy and one of the forms of calculating enthalpy. Now, the other forms of calculating enthalpy have to do with enthalpy of formation and enthalpy of combustion, which we're going to talk about today in these tables that are provided to you. And so the first table you have here is um, the thermodynamic data of very common organic compounds. And so you've got three different things here. The first being delta HF. Okay, delta HF is there's a symbol here, so it's standard. So it's the standard enthalpy formation. And all SL and HL needs to know this concept, hence why it's in red and orange. Knowing what it means and knowing how to write a reaction that describes the enthalpy of formation. So the first thing is the energy required to make 1 mole of substance from standard state elements at standard conditions. Okay. So the definition of enthalpy, standard enthalpy formation is the energy required to make 1 mole of substance from standard state elements at standard conditions. And what that means is this is one of those rare scenarios where you can have fractional coefficients because your limiting factor is that you have 1 mole of product, whatever you're talking about here. So, for example, methane would look like this. Okay. But ethane, actually, hold on. Let's see. I wanted to do one. Let's see. Oh, we'll just say, like, for example, water would be something like this. Okay, where you have a fractional coefficient because you can only make 1 mole of substance. Okay. So these values are given your enthalpy of formations. Now, what you'll notice is because the left side is all elements, the product side are all the species that you want. So when you're using enthalpy of formations, all the species that are in your products or your overall reaction are already on the correct side. All the species on your reactants of the overall reaction are on the wrong side. So you have to flip those equations. Hence why it's products minus reactants. Because the reactants are having to be flipped in these enthalpy of formation reactions. Okay, so it's products minus reactants because the products are on the correct side and the reactants of your overall reaction are on the wrong side, so they get flipped. And you do have to multiply by the coefficients as well in that scenario. So just keep that in mind when you're dealing with that. Questions about that? Okay. Now, also a great thing about this table is the amount of organic naming that is available on this table in case you forget how to organically name. And so that's the big thing here, because if you notice here, the first 6 main roots of organic naming are here: meth, eth, prop, bute, pent, and hex. C1, C2, C3, C4, C5, C6. So if you're having trouble remembering things, this is a great kind of cheat sheet for you to refresh your memory about things. For example, ethene has a double bond. Cis-butene, that would be for higher level, where you have the different arrangement of the carbon groups around the double bond. Ethyne is a triple bond. Butyl-1,3-diene represents 2 double bonds. The di representing that there's 2 double bonds as well. Okay, and so you see a lot of these different names here. Propanone is your ketone. Ethanol, methanol, your aldehydes and your carboxylic acids here as well. And notice that not only do you have the naming of that, but you also have the structural formula of those things as well. So in case you forget how to write an aldehyde, there's a reference for all of this in here. And notice as well, you've got water and steam. Depending on your reaction, pay close attention to the state of matter, because you may be producing liquid water or gaseous water, and that will affect your delta H as well. But you'll notice a lot of these calculations in a combustion reaction. So you'll be producing H2O and CO2 and things like that. And so really pay close attention to that. But yeah, a lot of your naming is already done for you in this table here. Now, one more note I forgot to say is that because delta HF is for production from standard state elements, we assume that our elements have a value of 0. So the standard enthalpy of formation of elements are all 0. So that is safe to say here. Okay. Questions about that? Now for higher level, you have to also be familiar with delta G, Gibbs free energy, and S, entropy. Okay, so notice that you're given values for this as well, so that you might have to use it in the equation delta G is equal to delta H minus T delta S. Or you may have to solve for the overall reaction, which is, again, products minus reactions, just like delta H. Units are really important. Like we said on part 1, the S is in joules per mole Kelvin, whereas the delta H is in kilojoules and delta G is in kilojoules. So you're going to have to do some conversions to make the S match the delta G and the delta H unit-wise. You'll also notice that S is never 0, because entropy of 0 means that you're at absolute 0 with no more movement. So S is always going to be a positive number. Now, delta S might be negative or positive based on the change in entropy, but the S overall will always be positive, because you're always going to be increasing randomness when you produce this, when this substance versus absolute 0. So S is never 0 or less than 0 in its own right. But when it's a difference in S, which you might have to calculate for this delta S here, it could be negative, because you could be increasing order instead of disorder. Okay. Questions about that? Now, this next table is enthalpy of combustion. Okay. Now, enthalpy of combustion is the energy change when 1 mole of fuel is combusted with oxygen. And it's kind of redundant, but that's okay. So to write a standard enthalpy of combustion reaction, the key is that you only have 1 mole of fuel. So whatever you react with the oxygen has to have a coefficient of 1, which allows you to have fractional coefficients in other places. So like C2H6 would produce this overall reaction. So you can have 7 halves in here. And we're dealing with mostly organic substances here that produce CO2 and H2O undergo complete combustion. So all of these formulas you want to imagine with oxygen to form CO2 and H2O. You'll notice as well, you could label this as the enthalpy of formation of water or the enthalpy of combustion of hydrogen gas. Either way, they're actually do the same thing by both definitions. Now, if you think about it this way, though, everything you want, the species that are in your overall reaction, if you're going to use this to solve for delta H of the overall reaction, all the species that you want are on the reactant side. Hence why this is reactants minus products versus delta HF, which is products minus reactants. So I like to know, okay, what's the definition of enthalpy of combustion? Can I write an enthalpy of combustion problem? Can I write an enthalpy of formation problem for one of the substances? And then I ask myself, where is the substance that I want? Is it on the product side or the reactant side? If it's on the reactant side, that means all my reactants are going to stay the same side. My products will change. If what I want is on the product side, then I will flip all the reactants and make them negative. So that's why it's products minus reactants. And notice all these combustion reactions are all exothermic. Because one of the definitions in IB chemistry is that all neutralizations and combustion reactions are exothermic. So again, in this idea, if you see a combustion reaction, you get a positive delta H, you probably subtracted the wrong side because you should be getting in a negative value for delta H overall. You should be getting a negative delta H of the reaction. RXN is the abbreviation for reaction. Okay. Questions about that? Again, yes, yeah.
Sorry, could you explain real quick why it's R minus P for this one as opposed to the other one?
Sure. So we have to think of it in terms in Hess's law. Okay. Remember Hess's law, when you add reactions up, you flip reactions to make it match the overall reaction. Well, in all the enthalpy combustions, everything that you want for your overall reaction will be found on the left side because this O2 and this CO2 and this H2O, they're all standard. They're all going to cancel each other out. So what you want is the C2H6 when you're using this. And if C2H6 is on the reactant side, that means if it's in the reactants, the overall, it'll stay the same sign. But if that C2H6 is on the product side in the overall, that means you'll need to flip this reaction. Hence, the delta H will change sign, which is why it's reactants minus products.
Okay, yeah, that makes sense.
Okay. It's just kind of an easier way to remember it than just memorizing reactants minus products, because if you get it backwards, you won't know whether you're right or wrong if you don't understand what you're doing. And so, yeah, that's the way I think about it. If I can write one enthalpy of combustion and one enthalpy of formation, then I can think, okay, where is the species that I want? Is it on the product side or the reactant side? If it's on the product side, then all my reactants need to change sign. If it's on the reactant side, all my products need to change sign. So I guess really it's reactants plus a negative product, if you want to think about it that way, the way I was saying here, because you're flipping all the products around in this case. Okay. Higher level, this is transition metals. And this is mostly talking about transition metals and the fact that they have multiple oxidation states. So knowing these variable oxidation states allows you to make various compounds with this. And so they're just kind of showing you the different ones to maybe ask you to make 2 or 3 different possible compounds with like oxygen or something like that. But here you're just showing that most transition metals have at least a +2 and then other oxidation states as well. Okay, but these are the most common, and I think one or two of them are also found on the periodic table that you see up here with the ionic radius. You can see like copper's 1 plus and 2 plus, nickel's 2 plus, iron's 2 plus and 3 plus, but you can see all the different common ones here for that. Okay. The spectrochemical series, is with ligands. Okay, so in complex ion formation, and this is higher level, you have a metal ion and then your ligands, which are electron-rich groups, which you can also know as nucleophiles, or you can also known as Lewis bases. Okay, they're all like, if you talk about it in terms of topic 8, or you talk about it in terms of topic 10, or topic 13, I guess 18, 20, and 13, they kind of take on different lives of their own. But the idea with this is the energy difference changes color of complex, because what the ligand does, it splits, it changes the distance between the split D sublevel, and that difference is what causes the energy to be absorbed to be different, which means the light that's transmitted or not absorbed is a different wavelength and frequency and energy. So this is why the colors change with these complex ions. So the highest one absorbs highest energy color, and then this one absorbs lowest energy. And then you see the complementary color of that. And we'll see a color wheel on the next couple pages that will reference that as well. But so the ligand itself affects the distance between the split D sublevel, which affects what color is being absorbed and then what color is reflected. There are 3 factors. It's the ligand, the metal ion, and the charge of the metal ion. Okay, so those 3 factors kind of all together affect what color you see for the complex ion. Okay. Questions about that? Okay. And this is a couple of examples of ligands here. You're going to see that these areas here are the points where you have that those bonding sites that can create an attachment to it. Okay. Okay, so like, because I was trying to figure out if all 6 sites of the EDTA lone pairs were ligands, but yeah, these all can bind to a metal complex and surround it. So y'all may have done your IAs on that and the fact how it binds to calcium and things like that. Here's the color wheel. Okay, you transmit the complementary color that is absorbed. So whatever color is absorbed, the complementary one, the one across from it on the color wheel, is what you see. If you absorb violet, you'll see yellow. If you absorb red, you'll see green. Okay, and that's what explains the different colors of the complex ions. That's why copper, chloride, and things like that is tend to be a blue color, because it's going to absorb kind of lower energy with the chloride here, and so it ends up absorbing orange, and you see blue. Okay. So different ligands will affect that here. And also notice you have the wavelengths of the different color ranges here. Violet being 400, red being 700, which means violet has the highest frequency and then the highest energy. So again, wavelength is proportional to, 1 over frequency, and frequency is proportional to your energy here. So another kind of concept with colors in that case. Okay. Questions about that? Okay. Also another higher level topic here. Okay. Lattice enthalpy. Now, what's nice about this is they actually tell you what lattice enthalpy is in the data booklet. They actually give you the reaction of what lattice enthalpy is. It's the endothermic process where you're converting a solid ionic lattice into gaseous ions. So all these values are going to be positive because it's the energy it takes to break all of the ionic bonds. And so you'll see that these values, all provided here, are obtained by the Born-Haber cycle. So they were using different other information like ionization energy, enthalpy of formation, electron affinity, atomization, things like that, to figure out what the lattice enthalpy is. Now you'll see that there is a large group here of your alkali metal halides, group 1 with your group 17. And then you have your other ones here, like your group 2s with 17 and group 2s with 16 and other varieties as well. And you can see that there are a couple of factors that determine your lattice enthalpy strength. One, the charges of the ions. And two, the ionic radii. Okay? Now, the charges of the ions is priority, and the way you measure it is you do the product of the two charges. So, if it's -2 and +2, or actually I should write it in the correct way. If it's 2 positive and 2 negative, that's better than 3 positive and 1 negative. Because you're in physics, you know that strength of attraction is based on the product of the two charges. And so the Q1, Q2 is kind of similar to that, divided by R squared. Is that kind of same idea here. So the charges get priority, but if the charges are all the same, then you go to radii. Smaller is better. Because the smaller the ionic radii are, the closer they are to be able to get to each other, which means a higher strength. So if you see here, like, let's see, something like beryllium to calcium, they all have the same charges, but because calcium is getting bigger and magnesium is bigger than beryllium, they both have lower lattice enthalpies than beryllium chloride. So pay attention to that. Charges have the most significant amount. Look at how big things change from group 2 to from group 1, like BeCl2 versus LiCl, right? 864 to 3033. So there's the biggest impact with a charge, and then if there's a tiebreaker, you go by ionic radii. Questions about that? This is also HL, I'm sorry to say. And so the enthalpies of aqueous solutions is what you're looking at here is the energy change when the solid goes to aqueous. And this is a new curriculum thing. This is one of the new things that was added to 2016 that wasn't on here before 2016. So if you find older papers, you're going to find you won't find questions about enthalpy of solutions in there because it's a new topic for this cycle. So enthalpy of solution is again that energy change when the solid salt goes into aqueous ion form. And it can be positive, it could be negative. Okay. And again, you can see that there is a change in energy based on the trends here. As the ions get bigger, the energy released gets more and more as it dissolves. So like things like lithium fluoride to chloride to bromide to iodide, the energy released when they dissolve increases because of the weaker the attraction there.
Mr. Brown?
Yes.
So, do we assume that the solvent used is always going to be water?
Yes, that's a good question. We are assuming that here all of them will be water. Correct.
So, wouldn't that be the enthalpy of hydration, or is that different?
That's different. So enthalpy of hydration, and we're going to get to that in a second, Alejandro.
Okay.
So, no, it's okay. It's a good question. So here's what this has to do, and we'll go back to this page in a second because I think the reason why IB implemented this in is because they wanted to show more energy cycles, and the Born-Haber cycle was too complicated of a cycle that they didn't want to ask that question every single year, and so they came up with a smaller cycle, and this is one of those examples because to to get there you can do it one of two ways. You can go straight across, or you can actually make them into gaseous ions first, which is your lattice enthalpy, and then your hydration this way. So, like Alejandro said, hydration is involved in here because hydration is the gaseous ion going to the aqueous ion. Okay, and that will always be negative. So the hydration will always be negative because it's always going to release energy when it's dissolved in water from gaseous state. It's always going to lose energy. But so this is an example of an energy cycle. So solution is solid going to aqueous. Hydration is hydrating gaseous ions and forming them into water, putting them into a water solution. Does that explain it, Alejandro?
Yeah.
Okay. So this is another example of an energy cycle that the IB might incorporate in here to show that you understand how these different enthalpies add together, but not in such a complicated way as a Born-Haber cycle, which requires 6 different energies, whereas an enthalpy of solution only requires really 2 or 3. I guess 3. 2 hydrations and 1 lattice enthalpy. So that idea here is another example of a small energy cycle. Okay. And again, here, all your enthalpy of hydrations, they include polyatomics in here as well. I'm not exactly sure why they do that, unless they would give you more information later on in the problem. Okay. Strengths of organic acids and bases. Now, I would say that for SL, you do want to know your different acids, okay? You may not need to know pKa's and things like that, but you do need to know your different general acids, methanoic, ethanoic, propanoic, butanoic acid, to understand your chemical formulas and reading the formulas correctly. Notice there's, anytime you have a CH3 parentheses 2, that's a branch. It branches off from the same carbon in that. So 2-methylpropanoic, it branches off of that. So this is this because your propanoic acid is this. Oops. Your propanoic acid is this, and your methyl group is branching off of that second carbon. So make sure that you're interpreting that correctly. Now for HL, again, pKa is negative log of Ka, and they tell you that, base 10 and things like that. And what you need to understand is that this relates to the strength. And it's kind of confusing because pKa is negative log, so it trends in the opposite way of what you might think it is. Because Ka, the larger the Ka, the stronger the acid, which makes sense because a larger Ka means it dissociates more, which tells you the strength of the acid. So the more the acid dissociates, the stronger we consider it. But when you take the negative log of that, it inverses your thinking. So therefore, you want a lower pKa to get a stronger acid. So methanoic acid is the strongest of these acids listed here, and 2,2-dimethylpropanoic is the weakest one. So larger Ka, stronger acid, but then when you take the negative log of that, that negative inverses things. So the smaller the pKa, the stronger the acid is. Questions about that? Okay. You could also note bases here and also still higher level. PKBs work the same way. The lower the PKB, the stronger the base. So Ka and Kb relate to their specific types of substances, and the lower they are, the lower the pK is of that species, the stronger it is. Ammonia and methylamine are the ones that I would know for higher level and standard level. Those are two of the most common weak bases, because amines are weak bases. Those are two most common ones that you use in reaction writing and things like that. So know ammonia, methylamine pretty well. Understand like the degrees of your amines. Like, for example, dimethylamine and trimethylamine is a second degree and a third degree amine based on how many things are grouped to the end. So you can understand that, but for SL, it's more of the structure and name. HL, it's understanding the pK of that. Like, I could see them having you do a titrate, like having a titration curve of a weak acid with a strong base, and then understand, like, you have to read halfway to the equivalence point to find the pKa, and then they might ask you which acid of the carboxylic acids here best represents that. So maybe you find the pH at the halfway to the equivalence point to be like 3.7, then methanoic would be your best bet. Now, it'd be hard in the 4.8s because it'd be really difficult, but I feel like they'd make it very significant one way or the other so that there wasn't any question about which acid it was. Because, I mean, these are all really close, so it'd be kind of hard to distinguish. But I feel like they would give you choices there that you could use. Okay. Acid-base indicators. Okay. Now, remember, acid-base indicators are essentially weak acids that change color in pH. And so these acids are used to indicate when a reaction is neutralized, because you want to choose an indicator that has a pH range that matches the expected equivalence point. Okay, so you want an indicator that changes color around where you expect the equivalence point to be. So if you have a strong acid plus a strong base, you expect that equivalence point to be 7 because it should be neutral. If you have a weak acid plus a strong base, it should be greater than 7. If it's a strong acid plus a weak base, it should be less than 7. So determining this based on that information allows you to choose the appropriate indicator for that. Now, what you have to remember is that this color change, the idea of acid and alkali, is not what we call acid and alkali. It's relative to this pH range. So when I say it's red and acid, that means it's red when it's less than 3.1, not 7. And it's alkali when it's yellow when it's above 4.4. So somewhere in between, it's orange. Okay. So understand that pH range fits in the middle of the acid-alkali column, and it's not based on 7 for neutral water. It's based on that. And we do usually use phenolphthalein even though it's 8.3 because it's easier to tell. This is why whenever you do titrations, they say, look for a really, really faint pink. The faint pink kind of hedges your bets toward 8.3, so you're closer to the equivalence point. But it's just easier to read than phenol red, which changes at 6.8 to 8.4, when you have a yellow to a red where the orange is really hard to differentiate, or even the yellow, blue, green color that is from bromoethyl blue. So we use phenolphthalein out of ease, not necessarily out of accuracy. Because if you really wanted accuracy, you wouldn't use an indicator only. You would use a pH probe in there, and you just use the indicator to know when to slow down, and then you'd use the probe to digitally graph the titration curve out, and then you could actually calculate the equivalence point. You can actually take the second derivative of the pH curve and find the point of inflection, and then find what the exact equivalence point pH is. Now, you're not going to be expected to do that because I can feel all of y'all's like calculus brains like cringing right now, but it is possible. And there is a program in Vernier Logger Pro that can do it for you. Like there are labs that are preset that actually can convert your graph and figure out exactly what the equivalence point is. But for our purposes, you'll just be able to guess it and use your best measurement to figure it out. Higher level, values of the ionization constant of water. For a higher level, Kw can change. For a standard level, Kw is essentially 1 times 10 to the negative 14, so therefore your pH plus your pOH equals 14. For a higher level, pH plus pOH equals pKw. So because Kw changes, neutral pH changes as well. Okay? And you'll notice here that the IB has now, in this new data booklet, written everything times 10 to the negative 14th for ease of reading. Because in the old data booklet, they'd have 10 to the negative 13th and 10 to the negative 15th later on. 10 to the negative 15th up here and then 10 to the negative 13th down the bottom. And for some students, it was confusing and they weren't able to kind of read clearly the exponents. So the IB has now made it so that even though it's not in correct scientific notation, it is very obvious that the K increases from lowest temperature to highest temperature because they've written everything in terms of 10 to the negative 14. Now, this ionization constant of water is essentially H2O dissociating into H plus and OH minus. Now, the one thing I would say from this idea for SL is that understanding that the ionization of water is endothermic because K increases as temperature increases, which means that as you increase temperature, it dissociates more. And the only way it can dissociate more is if heat is on the reactant side. So when K increases and temperature increases, that tells you your equilibrium is an endothermic reaction. For a higher level, you may have to figure out what pH of neutral is. And so at neutral, pH is equal to pOH. So this would be 2x equals pKw. So then pH of neutral is pKw over 2. So as you go higher and higher, your pH actually decreases neutral. But that doesn't mean that it's getting more acidic. That means the concentration of H plus is higher, but it also means the concentration of OH minus is higher. So it's not getting more acidic, there's just more H plus in there, but it's canceled out by more OH minus as well. So be careful with that concept. So if you're at a different temperature, 7 pH might end up being a base as opposed to 7 being neutral at 25 degrees Celsius, where it's 1 times 10 to the negative 14. So really be careful about that. And also you can think of it as H plus times OH minus is equal to KW as well, if you want to think of it in those terms. Okay. Questions about that? Okay. This is also for higher levels. So this is calculating cell potential of voltaic cell. Okay. And so here you're given all your reactions. Now, again, I don't like this title here because I think it's kind of misleading. And sometimes students read that and like misunderstand what it's trying to say. Like, because they're writing it in terms of what's happened, not what is happening. So it's really confusing for students because they'll see oxidized species like, well, lithium's gaining electrons, so why would it be oxidized? It's not. In that case, what they're saying is that lithium was oxidized and then it reduces by gaining electron and then it produces Li, which is your reduced species. So don't kind of look at that title if you want to avoid confusion. I don't like that title at all. So what you need to understand is all of these reactions are reduction reactions, because all of them involve electrons being gained on the left. So these are all reduction reactions. Don't think about oxidized and reduced species. It's really confusing. But what you can see here is a negative EV means a very poor reducer. And a positive means a very good reducer. Now, a poor reducer just means that it's a good oxidizer. So Li is a good oxidizer. Li plus is a poor reducer. And that's the way you want to think about it in this context. And because you're going to really make sure you have to differentiate between which species is reducing and which species is oxidizing. So Li would be a good oxidizer. Li plus would be a bad reducer. Questions about that? Okay. Now, to get your cell potential here, you add your reduction plus your oxidation reactions. Now, remember, I have you flip the oxidation reactions, so therefore you add the values together afterwards. But some books will say reduction minus oxidation because the minus already factors in the flipping without you having to flip it. I like to flip it because I have to flip the reaction anyways to add it. So I like doing that instead of just doing minus in there because I think it's more confusing. So you do have to flip a reaction and add the values together. If your cell is positive, then the reaction is spontaneous. Okay. So if your total E cell is positive, reaction is spontaneous. Okay. Couple of other things you want to look at here. Okay. Pay close attention to the different oxidation reductions that are happening here. Because, for example, iron can reduce from 2 plus to 0. It can reduce from 3 plus to 2 plus. And it can reduce from, isn't there a 3 plus? Oh, sorry, is there not a 3 plus to 1 plus? Or 0 plus? Oh, I guess they don't have that here. Copper, I guess, is the one I was thinking about. There's 3 of them here. Because copper can go from 2 plus to 1 plus, 2 plus to 0, or 1 plus to 0. So be really careful when you're reading this chart which species you're talking about that's reducing or oxidizing in this scenario, because there's a lot of different transition metals that have more than one value. Okay. Now the last thing on here is the fact that for electrolytic cells, cells of aqueous solutions, what's nice is the IB actually provides you the reactions of water for its oxidation and reduction. If you look closely here, water's reduction is right here. It's water gaining an electron to form hydrogen gas and hydroxide. And down here is water's oxidation. Water, think of the reverse reaction. Remember, you want to think about the reverse reaction here. Water is producing 2 electrons, 2 hydrogen ions, and then 1/2 O2 molecules of gas here. So these 2 highlighted reactions are the ones that you need to know for this, for electrolytic cells. So they're provided to you already in here. Now, should you still know them for the multiple choice? Yes, but in case you forget, they are available to you in the data booklet for short answer. Okay. Questions about all of that? The activity series. Now, this is SL as well, okay? The activity series is kind of a simplified version of the standard reduction potentials, but with just metals here. And you're looking at how reactive or how good of an oxidizer is a metal, okay? And so this is used for single replacement reactions. So this is when, will a metal replace a metal ion in a salt reaction? And so when you do this, you have to look at is Cu more reactive than Ag? And so the way you read this is the most reactive one is at the top. So you look here, Cu is above Ag, which means Cu is a better oxidizer, which means Cu will displace silver and make silver reduce. So essentially you're asking yourself, is the metal that's by itself a better oxidizer? Can it force the metal that's in the compound to gain its electrons that it's losing? And if it's more if this is more reactive, reaction occurs. Okay. If it's less reactive, then there's no reaction. So you would write no reaction as your products here. So when you look at this, you go, is this metal a better oxidizer than the metal that's already been oxidized in the compound? If it is, it'll force the metal in the compound to reduce to replace it in this. Okay. You can see a couple things here. H, essentially the acid, the acidic hydrogen from an acid. So most of these metals below H don't react with hydrochloric acid and things like that. The ones above H react more a little bit, And then these up here react very, very vigorously with your hydrochloric acid. Okay. Questions about that? You will need to balance this reaction and write the right compounds for your products and things like that, but I'm just trying to show you how the reaction would work. I'm not looking for accuracy in that case. Questions about that? Okay. This last part is the last thing that we talked about in the most recent topic, which is analysis of organic chemicals. And so the first table here we talked about was infrared data. And so here, this has to do with absorption due to bonds. So this is the one that has something like this, where the absorbance creates kind of upside down peaks to show you what types of bonds there are. And then there's a fingerprint region in this section for you to cover as well. Okay. So understanding this, again, fingerprint region kind of happens right about here. But sometimes they might reference the CO bond in the structure as well. But pay attention closely about your OH with the carboxylic acids versus your OH with alcohols and phenols. So there's a difference in OHs, and you'll notice here the broad versus like kind of just strong peaks here. Broad meaning wide, strong meaning very absorptive, and it goes down further on the graph itself. HNMR data, again, this is talking about chemical shifts. And so this is where you have those kind of sets of peaks here. Like this. And your shift tells you what type of hydrogen it is. Now, notice that they are bolded. It's not bolded very, like, obviously, but there is a amount of bolding that represents the hydrogens on each of these and where the hydrogens are located. So read very carefully, because a hydrogen on this side of an ester is different than a hydrogen on this side of an ester. So make sure that you're reading the compound correctly, because you will get different values here, 2.0 to 2.5 versus 3.7 to 3.8 on this. So it's important that you kind of are able to identify which hydrogen that they are talking about particularly. And don't forget, for some reason, there's two more on the other side. There's the benzene hydrogen, and then also the aldehyde on here as well. Okay. Now here, the mass spectrum, this is the one where you have kind of peak, 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 and peak. And this is where you have your parent ion peak, and these are your fragments lost. These are your most common fragments lost. These are not charged. But these peaks that are shown to you on the mass spec are charged, because only positively charged species will make it to the end of the mass spec and be detected. So if they ask you what species represents that peak, you would write the whole species with a positive charge. But if they ask you what fragment is lost, then you just write the fragment lost and you don't write a charge at all. So keep that in mind when you're doing this. Now, this table I put in here, but I don't think it's a huge application for this. I think this is a little bit more analytical, but I still think it's interesting, because if you remember, we talk about the types of bonding based on the difference in electronegativity. And so you can see that if you look at the difference in electronegativity here, you can kind of see how the bonding occurs. And so this is a little bit more of a three-dimensional aspect of it, where like you have a graph of electronegativity difference, and then you have the average electronegativity of the two values here. And so if you take those two factors, you can kind of plot on here, A, what type of bonding it is, and B, how much of it's ionic and how much is covalent. And so if you have a high electronegativity difference and your average is about 2.2, then you'd say it's ionic, and you'd say it's about 30% covalent and then 70% ionic. So a fairly ionic material. Now down here, maybe you have two nonmetals which have a low difference. Then you would have mostly covalent. Okay. Now, again, I think this is just to kind of help you review and remember what type of bonding there are. Don't use this table triangle for everything, but it is a good kind of a reference for that in case you forget, okay, how do I figure out what type of bonding I have in my molecule by looking at electronegativity difference here. It kind of helps you sort or categorize a substance into the type of bonding. Okay. And that is actually the end of the data packet for as long as y'all are concerned. Table 30 and on is all optional material, and since we don't have optional material this year, we won't need to cover any of that. And so you will not need to be flipping back to the last 10 pages of the data booklet. Okay. So yeah, that is it for the data booklet for review and things like that. Like I said, we'll dive deeper into some of these topics that I talked about in specific topic reviews, so that way you can kind of make sure you understand it more. But the idea of this project and this tutorial was just to kind of go, this is the information that you have. What can you use to your advantage to minimize what you have to memorize and help you understand and use the data booklet to their full potential? Because I think a lot of students don't realize how much information is in data booklet. They don't realize that a data booklet can help you name organic compounds. They don't realize that the trends are provided for you in all the periodic tables that are in there. And so really, really useful. And if you're not using it to maximum potential, then you're not making your life as easy as possible. And so that's why I wanted to spend these 2 days going over it, so that you could be aware of all the information that's present in here and do with it what you will to get ready for the IB exam.